Okay, so today we're going to do notes 12, 4, 5, 6, and as you can see, 7, there's nothing from that section. So, quick review from 12.3 is you were supposed to ask yourself that same question. We asked what multiplies to the end number, and then we read the addition or subtraction sign next to it to the middle number. Okay, so for example, we took something like this. And we knew that when we're factoring it, we always have it in factored form. We say what multiplies to 9 and adds to 6. Remember, everything's positive. We know that the first sign always goes here, and the bigger number always goes here. Okay, so we have x and x. And because we're adding, what multiplies to 9 and adds to 6, both these signs have to be the same. And what multiplies to 9 and then adds to 6? Well, 3 and 3 multiply to 9, and it adds to 6. 12.4 is exactly what we had done in the past. Solving for the zeros. So, when we're looking at this, how many times does this parabola hit the x-axis? Hopefully you know it only hits once in the same spot. We ended up with two answers, but it only hits in the same spot. It hits at x equals 3. That's where the axis of symmetry is. That also happens to be where the vertex is going to be, because it only touches once, because both answers were the same. All right. So basically what we end up doing is factoring and then solving. Whereas before we had factored form and you had to know what the zeros were. Now we're going to have to factor first and then tell me what the zeros are. Okay. Now there is some extenuating circumstances. Meaning, there are times where it's not going to look like this, but it still is in factored form. Why? Because you factored. So, for example, if you had 3x squared minus 6x. Again, one of the ways we learned to factor was, is there a number I can take out? Hopefully you know the number I can take out would be 3. And is there a letter I can take out? Yes, I can take out an x. And that would leave me x minus 2. So one of the zeros would be 2. What would the other 0 be? Well, this is where the math comes in. Theoretically, what we're supposed to do is put 3x is equal to 0 because we're finding the zeros, and x minus 2 equal to 0. Well, we already know that if we've always put x minus 2 equal to 0, the answer is always its opposite. Okay? Because when you move the 2 over, now you start to understand, oh, well, that's why the number is its opposite. Because whenever I go to solve this problem, I would have to move it over to where the 0 is because I need to separate the variable and the number. Okay? Well, the same thing happens with this term here. Okay? So this ends up being 3x equals 0, which, hopefully you know, it would be equal to 0. So let's say they give you something that's already in factored form, and they ask you for the zeros. So in theory, if you were going to show the math, they would want you to write this as two problems and put both of them equal to 0. Now, in our heads, we know that this one automatically is its opposite. It's going to be negative 7. Showing it mathematically, you can see why now it's its opposite. It's going to be negative 7. This one's a little bit more complex. You'd have to move that over, and you get 2x equals 3. And then you'd have to divide both sides by 2, and you get x equals 3 halves. Yes. Okay? So understanding that when we put this equal to zeros, it's just like finding the zeros, and you have to know that finding the zeros is where the parabola touches the x-axis. Do all problems have to touch the x-axis? No, they do not. Well, Mr. Fraser, what would be one that doesn't? Okay, well, let's try this one. X squared minus 11 plus 11x plus 12. So we would read this to ourselves. what multiplies to 12 and adds to 11? Nothing. There's nothing that multiplies to 12 and adds to 11. Remember, all the numbers we're dealing with are positive, so 12 and 1 add to 13, 3 and 4 add to 7, 6 and 2 add to 8. There are no numbers that multiply to 12 that add to 11. So this parabola would be above the x-axis. Okay? So in other words, it would look like this. And why do I know it's above the x-axis? Well, because I know it goes up, and if it was below the x-axis, it would touch it. So it's above the x-axis because I know it doesn't touch it. There are no zeros. No zeros means it doesn't touch. Because it's going up, it has to stay above. If this was a negative x squared in front of it, that means it would be below the x-axis. Why? Because it's not touching. In order for it to not touch, it would have to be below the x-axis and go down. And those are the basics of 12.4. 12.5. 12.5 deals with something called the difference of squares. This is called the difference of squares because you have to be able to recognize your perfect squares. Many of you don't. I'll write them down. You have to study them because you have to see this is a very specific type of problem. So difference of squares are numbers that are perfectly squared. So you should know your perfect squares all the way up to probably 225. So it starts with 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 196, 225. Now my suggestion usually is writing these all down on your test. Pretty easy because you do 2 times 2, 3 times 3, 4 times 4, 5 times 5, 6 times 6, 7 times 7, 8 times 8, 9 times 9, 10 times 10, 11 times 11, 12 times 12, 13 times 13, 14 times 14, and 15 times 15. By having them written on your test, you now can visually go, oh, that's a difference of squares problem. So what makes difference of squares different? Well, the fact that the word difference is in there should tell you that you're going to have what type of problem? Should be a subtraction problem, correct. And it's a difference of squares, which means the first term would be squared and the last term would be squared. It's called a difference of squares. So it's a subtraction problem with 2 squares in it. Now these can look pretty extraordinary or pretty extravagant, but the concept remains the same. Whenever you have a difference of squares, the signs in the parentheses are going to be different because that's what we've talked about. Whenever we subtract, we have different signs. So that means one of these signs is going to be negative, one of them is going to be positive. So you square root it. X squared, square rooted, is x. 9 square rooted would be, correct, 3, because it's a perfect square. Ends up being x minus 3, x plus 3. You see it, you can cheat, you do it. It's automatic. Would this problem be a difference of squares? Yes. Why? 4 is a perfect square, x squared is a perfect square, 25 is a perfect square, and y is a perfect square. So I can do the cheat. You will notice that you will have the exact same thing in both parentheses, except one will be negative and one will be positive. The answers, the zeros, will be different because it's called a difference of squares. So this first term would be 2x. Why? Because I square root the 4 and I square root the x. It goes there. And the term that would go here would be 5y. Once I have the first one, the second one looks exactly like it, except for the minus and the plus. So again, it's 2x and 5y. These become a lot easier to factor just because it is a special cheat. it's called the difference of squares. So because it's called the difference of squares, you can do this process. You don't have to read it backwards. If you were to read it backwards, it would be, what multiplies to 25 and subtracts to 0? 5 and 5. Because there is no middle term. That's what makes it unique. You know that they're going to be opposites of each other because anytime you add opposites, you get 0. Yes. So this would be considered an easy. This would be considered a hard. It's just understanding what you're square rooting. Now, let's look at this one. Is this a difference of squares? And the answer would be no, because this is not a perfect square. If it was to the 4th power, then yes, it is a perfect square. If it was to a 6th power, yes, it would be a perfect square. If it was to the 8th power, yes, it would be a perfect square. If it's any even power, it would be a perfect square. But because it was to the 3rd, it isn't. Now I've changed it to the 4th. Now it's perfectly squared. So I square root it. 9 is 3. X to the 4th is x squared. So that's 3x squared. This one's minus, this one's plus. It doesn't really matter which one you put, but I always tell you to get in the habit. The first sign goes here, second sign goes there. All right, and then I do 16, which is 4 and y, and 4 and y. And there you have it, the difference of squares of polynomials. This is all based on, can you identify a perfect square? All right, then we get to our next one, which is, these are two special types of factoring problems. This is a perfectly squared polynomial, which you can use the cheat. And this is a perfectly squared polynomial. Perfectly squared meaning both answers are exactly the same because they're squared perfectly. And we still use our perfect squares. The reason I know this is perfectly squared is because this and this involve the exact same number. 3 times 3 is 9, and when I add them, I get 6, which means both of these will be x minus 3. Now you can write it twice still, but the idea is this is how you would write it in simplest form. Now, we've already talked about how many times does this problem actually touch the x-axis. It only touches once. Why? Because it has the same answer. It's going to touch the same place at x equals 3. And the vertex would be 3, 0. Now this happens for any of these. We'll do x squared plus 10x plus 25. So I realize that this is perfectly squared, which is 5 and 5, and that adds to 10. So again, this is x plus 5 and x plus 5. Now you still go back and do the factoring rule if you want, that's fine. But then you have to realize that the answer would be x plus 5 squared. And your axis of symmetry would be x is equal to negative 5, and your vertex would be negative 5, 0. Now would that vertex be a maximum or a minimum? Hopefully you know it would be a minimum. Why? Because the first sign is positive, which means the parabola goes like this, which means the point there that's the vertex would have to be the minimum. All right, that's it for 12.5. We move on to 12.6. 12.6 involves square rooting. This is pretty easy. Every time you square root, you end up with 2 answers. Okay, so for example, if I said, what is the square root of 9? The answer is always 3 and -3. Every square root has 2 real number answers. It's positive and it's negative. So it's understanding that every time you square root something, you end up with 2 answers. These are just square rooting rules. These actually don't have a whole lot to do with the factoring. It will have to do with what we learned in 13, the quadratic equation. So in actuality, if you want, I'll write down the quadratic equation now. It's only the only thing we learn in 13. It's called -b plus or minus, which means you're going to have 2 problems, right? Everybody knows whenever we square something, we have 2 problems. Of b squared minus 4ac all over 2a. And there's a great little song that goes with it. It's a Pop Goes the Weasel song. It goes, x equals -b plus or minus the square root of b squared minus 4ac all over 2a. Now, do you have to remember it? Nah, because they put it on the reference sheet. But you do have to know how to use it. You'll plug in numbers and then solve. The idea is making sure you plug in all the numbers correctly. And we'll go over that when we get to 13. But notice it's plus or minus. Why? Because every time we do a square root problem, the answer is either positive or negative of the same number. Even if it turns out to be a decimal, it's still positive or negative of the same number. So understanding that when you square root, that you could have 2 answers is really important. Understanding that when we write a radical, you have to know what the pieces of the radical are called. Like this is a radical, then there's a radicand. The radicand is inside. Okay. So you have a radical, this is the radicand. Radical, radicand, radicand. You should know the difference between an expression and an equation. An expression has no equal signs and an equation does. If I were to square something really goofy, like 75, square root of 75 does not square root evenly. Let me put that up here. Square root of 75 does not square root evenly. So I try to find a perfect square that goes into it. This is what we call simplifying a radical. And I'm not going to get in depth of that. Why? Because on any kind of test, if you simplify the radical, you can find the other radical expressions and put them in your calculator and you'll get the same answer. So that's how you know what it is. Technically, what you're supposed to do is split this up into the square root of 25 because 25 is a perfect square. That goes in. And you always find the biggest one. And then, obviously, the other one would be the square root of 3, and this would be 5 square root of 3. Now, we'll go into this more in depth later. But it is understanding, basically, that whenever you square root, it's the opposite of squaring. So 3 times 3 is 9. The square root of 9 is 3. They're forwards, backwards, the reverse operations. All right. Well, thank you very much for listening, and hopefully you continue your 12-3 work and you finish that for tomorrow. Thank you very much.